In this video, I want to talk about a subject that is very, very important, but also very intimidating when people think about linear algebra, and that is the idea of eigenvectors and eigenvalues. When we talk about eigenstuff, what we're generally talking about are the kind of core patterns represented by a matrix. So we'll be talking about some square matrix, let's say A, and let's take that to be an n by n. So this is an n by n matrix A. An eigenvalue and eigenvector of A are represented by the following relationship. A multiplied by some vector x is equal to a scalar lambda multiplied by that vector x. So in this case, x is the eigenvector and lambda is a scalar, which we call the eigenvalue. Eigenvectors are the kinds of vectors that when you hit them with a matrix, all that happens is that they get multiplied by a scalar. So even though we hit x with this matrix A, all that happened is that we multiplied it by a lambda. Now that lambda could be negative, it could be big, it could be small, but all that's happening is we're scaling x in some way. The reason this is interesting is because somehow x captures fundamental information about the matrix A. Now there might be many such eigenvectors for any given matrix A. In fact, you can see right away that it doesn't care about scale. So if I was to multiply A by instead some Cx, then that's just going to wind up on the right side as well. So a scalar multiple of any eigenvector x is also an eigenvector. It turns out that eigenvectors and eigenvalues come up a lot when we're doing different kinds of data analysis. In fact, one of the most important algorithms in all of machine learning and statistics is principal component analysis. And PCA is entirely about identifying the eigenvectors associated with the covariance matrix of the data you're trying to analyze. So to get a little bit of intuition for how that works, the idea of PCA is that we have some cloud of data. And let's imagine that it's high dimensional, but I'm just going to draw it in 2 dimensions for now. Imagine that we wanted to analyze these data and we wanted to somehow represent them in a lower dimensional way. Now it's 2 dimensions, so that means representing them in 1 dimension. Now, what we could do is project these data onto any line we wanted, and that would give us a one-dimensional representation of these points. However, when we look at this, what we can see is that there's one direction that's more elongated than the others. And so we might expect that that direction of large variance might be the one that's most representative of the interesting statistical structure in the data. And that's a good intuition, it turns out, for a lot of kinds of analysis that we might want to do, especially as we get into higher dimensional spaces. But how do we find that direction of large variance in a high dimensional space? Well, the answer is we look at the eigenvalues of the covariance matrix. We'll talk about covariance matrices in a couple of weeks when we talk about probability. But for now, what I want you to think about is just that we're going to model this elongated set of data via some ellipses. You can kind of imagine that that's some representation of the density from which these data came. And these ellipses are short in some directions and long in other directions. And the ellipses themselves are represented by a positive definite matrix. It turns out that if we look at the eigenvalues of the positive definite matrix representing something like this ellipse, that we would discover that they represent the long and short directions of these ellipses. And so what we can do is look at the direction, that is the eigenvector, that has the largest eigenvalue, and that will be the direction in the data of the highest variance. So this is a very important tool, and like I said, we'll come back to this, and in fact, you'll study it a little bit in the next homework. One of the other really interesting ways that we use eigenvectors and eigenvalues is actually to study things like social networks. Let me give you a little bit of an idea of how that works. Let's imagine that we have some graph, and let's say the vertices could represent web pages or Twitter or Instagram users, but let's give them labels A, B, C, and D. And let's imagine that there are directed edges between these vertices. These edges could represent links from one page to another, or they could represent the idea that A follows B on Instagram, whatever you want. Let's imagine that maybe A follows B, B follows A back, and maybe A follows C, and maybe D also follows C, and maybe C follows B, and we'll say that B and D each follow each other. Now, we might want to reason about how important these different vertices are. You could imagine trying to identify who the influencers are, and maybe the influencers would be the people who are followed by a lot of people, and in particular, if those followers are themselves influencers and things like that. Or on a web page context, you could imagine that a web page is very important if it is linked to by other important web pages. And so we might want to reason about the structure of the graph in order to decide which vertices are the most important ones. Maybe those are the ones we want to return as search results, say. It turns out that we can answer this kind of question by looking at the big eigenvector associated with the adjacency matrix from such a graph. Imagine that you're taking a random walk on this graph. So if we're sitting at vertex D, and this is a web page, and there are two outgoing links, then maybe you choose one of those links at random. Maybe you choose C, and then you are on web page C and you choose one of the outgoing links at random. In this case, there's only one. You go to vertex B, and so on. And you take a random walk over the vertices of the graph by clicking randomly on links on whatever web pages you land on. Now, if you do that, you'll be wandering around the graph. And if we imagine it's kind of densely connected, then maybe you can reach any given vertex on the entire graph by doing this kind of random walk. Then if we imagine that you do that for a very, very long time, then what will happen is you will converge to some distribution on the vertices. That is to say, some fraction of the time you'll be sitting at vertex B, and some other fraction of the time you'll be sitting at vertex C. And it turns out that that fraction of the time is exactly this notion of importance that you might want to be able to reason about. That is to say that if a lot of things are linking to some page, and a lot of things are linking to those pages, then they're propagating maybe importance up to that web page. Like if you're on Twitter and you're followed by Taylor Swift and LeBron James, then maybe that says something interesting about your importance to the graph. So the specific way that we figure this kind of thing out is a little bit more complicated, but the gist of it is that we write down the adjacency matrix of this kind of graph. And then we normalize it in such a way to reflect this idea that you're taking random steps along the edges of the graph. And then it turns out that if we think about the resulting Markov chain, that is the random walk that you're making around, and we look at the transition matrix associated with the Markov chain, the big eigenvector associated with that will be this measure of relative importance of the vertices. And that's actually a thing that you can compute even at scale by simulating from this kind of random walk. It turns out that that method of actually simulating from the random walk, you can think of that as what we would call a power method for computing the big eigenvector associated with a matrix like that. Now, this might sound very abstract and the kind of thing that nobody would actually do in practice, but what I've described here is actually one of the ideas that led to the Google search engine, an idea called PageRank. Now, I've left out some important details here, but the gist of it, the idea that importance propagates along links, is one of the reasons that Google search engine in the beginning had better search results than a lot of its competitors. And procedures like I described actually do inform the way that social media companies like Twitter think about the users on their platform. So again, the idea of an eigenvector is that it's a vector x associated with a matrix A, such that when we hit it with A, all that happens is that x gets scaled by some lambda. So this is a very useful thing to do from the point of view of pattern discovery, like I was kind of just talking about, but it also gives us a way to think about bases in which it's useful to do different kinds of computation. In particular, thinking about bases where A is diagonal. Diagonal matrices are really nice because they're really simple, lots of zeros, you can invert them easily, and they're quite straightforward to reason about. So when we can find a diagonal basis, that's usually a good thing. So what's the relationship between a diagonal basis and things like eigenvectors? As we said a second ago, let's imagine that A is a square matrix and that it's n by n. Let's imagine further that we've found n linearly independent eigenvectors. And let's imagine that we label those as eigenvector P1, P2, P3, and so on. And then let's take all of those and make them the columns of a matrix, and let's call that matrix capital P. Now what happens if we multiply our matrix A by P? So A is the matrix we're focusing on. The columns of P are the linearly independent eigenvectors that we found. What happens when we do this is we get a matrix that is going to be scaled versions of each of the p's. Because when we hit each column with A, then all that happens is we multiply it by the lambda associated with that eigenvector. So if we give them the same indexes as before, then we have now a lambda p1 and a lambda 2 p2, and so on. And we could actually think of this as multiplying p by a diagonal matrix where the diagonal is composed of these lambdas. What I mean by that is, let's imagine that we have a matrix, let's call it capital lambda, and on its diagonal is lambda 1, lambda 2, and so on, with zeros off of the diagonal. Then we can write this as p multiplied by that big lambda. So let's do that. So these guys combine, and we get a p equals p lambda. It's worth taking a minute, if you haven't thought this through, and thinking about how a diagonal matrix like this would scale each of the columns. So now when we're in this situation, what we can do is multiply on the right by P inverse. And we know P inverse exists because we have n linearly independent eigenvectors. So we know that this matrix is invertible. So we do that, and we get A, P, P inverse equals P lambda P inverse. And of course, these guys become the identity. And so we wind up with A equals P lambda P inverse. So we say that P diagonalizes A. It gives us a basis in which A is diagonal. So the idea of an eigenvector and the idea of diagonalization are very closely related. Being able to diagonalize a matrix makes life easy in lots of different ways. So if we have some A that we care about, and we find P's such that lambda is diagonal, then just hearkening back to the last video where we talked about determinant and trace, we can already see how life might be easier. So for example, let's think about the trace of A. So the trace of A, now we would write it as trace of P lambda P inverse. And we can use the cyclic property to move one of the p's to the other side, right? So we could say p negative 1, moving that to the front, p lambda. And so, of course, those become identity, and we just wind up with the trace of lambda. Now, that's particularly easy, right? Because lambda is diagonal, so the only entries it has are the ones that matter, and in fact, they're the eigenvalues that we found just a second ago. So that shows us that the trace is just the sum of the eigenvalues. We could do exactly the same kind of thing with determinant, right? We can also say det A, and just like that, we'll say that is equal to det of P lambda P inverse. Now, the determinant of a product is equal to the product of the determinants. And so we'll do that. We'll say det P, det lambda, det P inverse. And of course, this is 1 over the determinant of P. So just writing that out explicitly, we get det P. And of course, these cancel. And so then this is going to be the determinant of lambda. And the determinant of a diagonal matrix is the product of the elements along the diagonal. So this is the product of the eigenvalues. So you can see that there's a kind of sum versus product relationship with the eigenvalues that we get from trace versus determinant. And then there's one more way that a diagonalization really helps us, and that's with thinking about matrix powers. To give you an idea, let's just imagine that we wanted to square A. Well, that's just multiplying A by itself, of course, just like we're used to. Now let's write out the diagonalization. We would have P lambda, P inverse, P lambda, P inverse. Now these turn into the identity matrix. And so we get P lambda, lambda, P inverse. Or we could say P lambda squared, P inverse. And this is particularly easy because recall that lambda is again this diagonal matrix composed of the eigenvalues of A. So what this means is that all we did was square the eigenvalues of A. One of the key ideas that you want to be aware of when you're thinking about eigenstuff is the idea of the characteristic polynomial. Now our starting point for the characteristic polynomial is to think about our main property associated with an eigenvector and eigenvalue. That is to say that if I have a matrix A and I hit an eigenvector x, then all that happens is I scale it by some amount lambda. Now one thing I could do is throw an identity in here if I wanted to, because of course lambda is a scalar but A is a matrix, so let's solve that by writing this just slightly differently. We'll say AX equals lambda identity x, and now let's move this over to the other side to give us an equation AX minus lambda I x equals 0. Now what we can do is factor out the x, and we could wind up with an equation that looks like this. A minus lambda I multiplied by x equals 0. And the idea of the characteristic polynomial is to try to think about what we would call non-trivial solutions to this equation. That is, solutions to this equation in which x is not equal to 0. When would that happen? Well, that would happen when this matrix has a null space, or a kernel. So just to remind you, the null space, or the kernel of a linear transformation, is the set of vectors that go to 0 after applying that linear transformation. And so for this equation to be true, there must be some interesting null space. And if there's a null space, that means that the matrix is not invertible. That is to say that if there are some vectors that are not 0, and then you hit them with the linear transformation, and they become 0, there's no way to get back. You can't recover the information that you destroyed by hitting it with that linear transformation. So if it's not invertible, then we would say that it's singular. That is, it's a singular matrix. And a singular matrix is one whose determinant is 0. So if we wanted to solve this equation, then rather than thinking about the x's, what we would instead say is we're looking for the situation where the determinant of A minus lambda I equals 0. That is, situations in which there exists a lambda such that this is singular. It turns out that when you write this out, it will give you a polynomial in lambda. And then if you imagine factoring that polynomial, then it will have some set of zeros. And those zeros are the eigenvalues of A. Now, you can immediately see that because that produces essentially an arbitrary polynomial, it's possible that it won't have any real zeros. And so it's perfectly possible for a matrix to not have any real eigenvalues. Similarly, it may be the case that the eigenvalues are not unique, because we could have a polynomial in which there are lambdas that correspond to multiple zeros. Just to give a little bit of a flavor of the way this works, so we could imagine a simple case where we said A is equal to, let's say, 3, 1, 2, 2. Now, if we write out the determinant, that's going to be reasoning about the determinant of the matrix 3 minus lambda, 2, 1, 2 minus lambda, and finding the places where that is equal to 0. So let's write out the determinant of this. So it's going to be 3 minus lambda multiplied by 2 minus lambda minus 2 equals 0. Writing this out further, we get 6 minus 5 lambda plus lambda squared minus 2. So put another way, we get lambda squared minus 5 lambda plus 4. So we could write this out as lambda minus 4, lambda minus 1. And of course, the zeros of that are going to be 4 and 1. The characteristic polynomial also helps us understand a little bit more clearly how we might wind up in a situation where we don't have any eigenvalues. So here's one situation where that's true. Let's imagine we were talking about rotation matrices like you're doing in the homework right now. We might have a rotation matrix R in 2 dimensions that looks like cosine theta, negative sine theta, sine theta, cosine theta. Now let's think about what the eigenvalues would be for this matrix. So as before, we're thinking about the situation where we have the determinant of now R minus lambda I equals 0. So let's write this out. We want the determinant of a matrix that is now cosine theta minus lambda, negative sine theta, sine theta, and then cosine theta minus lambda. And we want that to equal 0. Let's write out the polynomial. Cosine theta minus lambda squared. Now plus sine theta squared equals 0. So you can see right away, just from this, that we're already in trouble for finding interesting eigenvalues for arbitrary theta, because this is a quantity squared plus another quantity squared. So both of these things will be non-negative, and it's going to be difficult for them to work out to be 0. In fact, you can immediately see that unless theta is 0 or pi, there's no chance that there's a real eigenvalue. If theta is 0 or pi, then cosine theta will be 1 or negative 1. And you can see then that for this to be 0, lambda will then have to be 1 or negative 1. So there's only 2 possible thetas in which it's possible to solve this polynomial, and in those cases, you get a repeated eigenvalue of 1 or negative 1. Another useful thing to know is that symmetric matrices are orthogonally diagonalizable. What that means is that the eigenvectors you get out are going to be orthogonal to each other. And remember that they're only unique up to scale, and so we can choose their length, which means that we get an orthonormal set of eigenvectors whenever we orthogonalize a symmetric matrix. To see why that's true, let's imagine that we have 2 eigenvectors, each that has a distinct eigenvalue. So let's imagine that we have some x such that we get lambda x when we hit it with a. And now let's imagine also that we have a vector y, and when we hit that, we get a gamma. Okay, so these are 2 distinct eigenvalues. Now we come along and let's say we hit this on the left with y transpose. So now we get y transpose a x equals lambda y transpose x. Now these are both scalars, so we can transpose scalars, no problem. So let's do that. Let's write x transpose, now a transpose y equals lambda x transpose y. And let's do the same thing over here. Let's imagine we hit this with an x transpose on the left x transpose A y equals gamma x transpose y. Now, note that because A equals A transpose, because these are symmetric matrices, then we have the situation where these things all need to be equal. So we have the situation where we now need lambda x transpose y. From that needs to equal gamma x transpose y. Now we already said that lambda and gamma are distinct eigenvalues, so they're not the same value. So the only way this can be true is if x transpose y equals 0. And if x transpose y equals 0, then that means that having distinct eigenvalues means that the associated eigenvectors are orthogonal. And as I said before, since we can scale eigenvectors however we want, we could make them unit length. And so then we would have an orthonormal collection of eigenvectors.